Good morning. Today, let's talk about electrostatic potential, or voltage, as we've seen earlier. So, a little bit underappreciated. Before we talked about electric fields, and electric fields give you force. They are a way of looking at force with a test charge. Take a test charge out. That way, you can scale up how much force based on how much charge you have. Voltage, or electrostatic potential, or sometimes just potential, it's a similar idea, but it's for work. So, when you're talking about force, you should think electric field. When you think about work, you should think voltage, or electrostatic potential. Another thing is vector, scalar, scalar. So, let's start off with a definition. So, if I had to give a definition of electrostatic potential, I would say something probably along the lines of amount of work required to move a positive test charge. And I say positive just to make sure I get the sign correct. Positive test charge from infinity to a given point, let's say point P. So the concept here, move a positive test charge from infinity to point P. And that's the amount of work required. So I'm going to look this up on Wikipedia real quick. I know Wikipedia is not the end-all, be-all of definitions and should be trusted only. Electrostatic potential. Trusted only as far as you can throw it. All right. So, the electric potential is the amount of work needed to move a unit of positive charge from a reference point. I'm going to call this reference point infinity. And they say down here, point inside the field without producing an acceleration. Okay, static. Typically, the reference point is the Earth. Yeah, okay. Or a point at infinity. We'll choose infinity. Although any point beyond the influence is work. Okay. Scalar, yep. And measure. Okay. So the key points here I'm going to take is work, positive charge from infinity. So let's do a sample problem using just this definition. So let's say we have a positive charge. That's always going to be blue. Blue is a very positive color. So we're going to have a test charge over here, which is positive. I drew it small. That way it can, I don't know. It feels appropriate that test charges are small. And so we have an electric field from this charge here. I don't know, we'll call him big Q. Seems reasonable. It'll be positive. That way the electric field lines go out. Electric field. So electric field goes this way. And we want to find the work required. I tried to draw it down a little bit lower so that we would get a good so it wouldn't overlap. Did not work. So we're going to take this test charge and we're going to move it all the way over here. So we're going to use the equation we've always used for work. So work equals mad. Work makes me mad. It doesn't actually make me mad. Work is the lifeblood of life, but that does not work as well as a mnemonic. So mad is more useful. So we rewrite mass times acceleration be force times distance, and we're like, well, let's be a little bit more specific here, and we'll do F dot dr, where work is the integral of the force vector dot the displacement vector r. Which I guess gets kind of confusing because it looks like, oh, there's distance there. No, that's actually the derivative, and right there is a dot product. Okay, Now in our example, we're going to move this point charge, this test charge, to this point charge directly towards it from infinity. So the angle between the two, draw kind of like this, and that'll be theta, will equal pi, or 180. So we'll go from infinity to, I'll call this test charge small q, and we'll go to a point A right here. We won't go exactly to each other because then we start dealing with dividing by zeros, and we don't want that. So point A. Did I say point P? It's okay. We're now going to point A. F, and this time we'll do times dr, and then we'll do cosine of theta, where theta here is pi, therefore cosine of pi is -1. So we'll get a -1. Yeah, I'll do that in the next revision. Okay. So we have negative infinity to A of K, Coulomb's constant, because we're using Coulomb's law now for force. Big K, that's the point charge. Little q, that's the test charge. And then we'll say r squared dr equals okay, I'll factor out everything that's a constant. R to the -2 dr equals k q r to the -1. Okay, so to integrate, add 1. So -2 goes to -1, then divide by what you divided by. And we have k q r. Why did I get that r? Where did that r come from? That r is not supposed to be there. That's supposed to be a little q. Little q over r, and the negatives and canceled. But then we're still from a to infinity, so this equals k q q over let's do it like this. Negative, negative. This will be then 1 over a minus 1 over infinity. Yep, seems good. I'm good with this. Okay. So then 1 over infinity will go to 0, and we are left with k q q over a, which equals the work required to move a charge from infinity to point A. All right, that says infinity A subscript there. Ooh, that worked out surprisingly well. Which, if we take out the test charge, Q, this would be written as VA. Or as I like to write it, Q V infinity A. With the idea being that you're going from infinity to point A. And this is the formula that you have for the voltage of a point charge, the potential, electrostatic potential. Those are all synonyms, by the way. I'm not saying different things. Boom, 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 boom. Yes. I feel surprisingly confident about that. Okay, so one thing you might have noticed is that we took right here is E. Oh, sorry, I should only have one Q there. Is the E, the electric field. And you'll see a definition of voltage as the negative integral of E dot dr. And the negative sign there might kind of confuse you a little bit, but the reason that exists is because what we discussed up here. And these should probably actually be vectors. There we go. And the dot product. So you get the negative because you're moving a positive test charge towards an assumed positive value. in opposite directions. And so you get a cosine of theta. You have a dot product moving with force moving opposite direction with the displacement vector in the opposite direction of the force. There we go. And that's where the negative sign comes from. So it's not randomly thrown in there. Okay. Now we're going to go over a little bit of notation, because notation, the hardest part about voltage or potential, because it's a scalar, so you don't have to worry as much about angles, but signs tend to get fairly confusing. And so how people ask the question is often half the battle. So we're going to go over a little bit of notation. So if I said voltage AB, that would mean voltage B minus voltage A. And your thought process might be, there's no really such thing as just voltage at a point. Voltage is a comparison of energy between 2 points. So that'd be like saying, what's the energy of like a ball? A ball, you have the ground here, you have a ball here, and I'd be like, well, what's the energy? And specifically, you'd probably be thinking of potential energy, which, okay, that works well. What's the potential energy of this ball that's, 2 meters above the ground? And you'd be like, well, mass times gravity times height. And that'd be reasonable. But what if I dug a hole? What would be the energy of the ball at that point? Well, the energy then would be, however far it was, maybe to the bottom of the hole. And you'd be like, well, that's kind of a silly, arbitrary way of making an exception. We have to work with some givens in life. That's true. But you have to be very careful about what your assumptions are. Same thing with gravity. When you're talking about potential energy of like a ball falling, you really need to know where the ball starts and where the ball ends. Saying, well, what's the potential energy of this ball is meaningless. Most of it, you can make assumptions and guesses, but you should do your best to get rid of all those assumptions when you can. Same thing with potential. The potential at a point is meaningless. So VB at point B really doesn't mean anything, but what's assumed that you mean is point infinity and then point B. So we can rewrite this as voltage AB equals, let's say, we're going to skip right down to we're going to use the equation negative E dot dr. Nope, I'm just going to use E dot dr. So, and then if we multiply both these by Q, our test charge, then we have the work. So this is based off, so this is asking, what is the work required to move a particle from point A to point B? And so we're going to rewrite this as A to B. And we have the extra Q's in there to make it work. And this is going straight off of our original definition, which I butchered up here, and then read off Wikipedia. Now, the problem with reading it off Wikipedia is there's a lot of other stuff there that really isn't that useful. Positive test charge from infinity. Okay, so I'm going to rewrite this slightly as Q times, let's go from A to infinity, E dot dr, maintain the vectors, that's okay, plus infinity to B, E dot dr. Okay, I'm good with this. And so all I did was I added an intermediary point. Now granted, if I draw this out, I'm going to draw this as, let's say we have our electric field here that's positive, and it's creating an electric field going this way. A, B, and I'll say infinity. So when I write it like this, you think, oh, infinity here. Well, could, but what I'm going for is infinity off towards the edge, you know, near infinity. Follow me here. Even if you don't believe me, we'll just kind of roll with it and see what happens. So let's see here. We still have our Q. We'll flip this one around. So we'll have infinity to B, E dot dr. I'm just moving it, minus infinity to A, E dot dr. Yep, flip the limits of integration, and so you flip the sign. And now I'll get rid of, probably should use a different color for this. I'll now choose to put in the negative signs, get rid of, there's supposed to be little vector symbols up there. There weren't. And so now we can see that we have VB minus VA, because this is the same form that we had earlier of finding the work required for a test charge from infinity to 0. So what this is saying, which equals Q VAB. So what this is saying, just cancel these out. I know, I keep getting you all excited and I backtrack slightly. That's just trying to convince you that voltage VAB equals VB minus VA. So if we zoom in here, VB is the energy required to go from infinity to B. And the VA is the energy required to go from infinity to A. So it's saying that VAB is VB minus VA. So if you look at how to subtract vectors, this would be I know voltage is in vectors, but bear with me. So you flip this around and you're going to get a vector that looks like this. So this would be negative VA, this would be VB. You add this to that and you're left with a little energy like this. So VAB. So the voltage A to B is the energy required to move a test particle from A to B, which equals the same as VBVA, which is the amount of energy required to move a particle from infinity to B, minus the particle energy required to move a particle test charge from infinity to A. So let's throw in some numbers, completely arbitrary, mostly arbitrary, just to kind of give a more intuitive feel. So if we have a test charge at infinity, you think, well, okay, what's the potential energy there? Can be whatever we want. We're going to say 0 because that's a general assumption for life. And that's also the assumption used on the AP exam as well, is that a charge at infinity has 0 potential energy. So if we move it to B, there would be some potential energy gained, and if we take that potential energy per unit charge, then we would have volts. So we could say at B it might be 6 volts. If we go all the way to A, then it might be 9 volts. And we're getting more and more energy as we're moving closer. So if we have a positive charge here and a positive charge here, the more we take these charges and push them together, the more energy we're going to store with that with those charges. So, one charge is fixed, take the other charge, move it towards it, we're going to have all this stored potential energy. we then release the charge that we're holding, and it's going to zoom off the other direction. How fast is it going to zoom off? Well, we're going to take that potential energy that we had, and it'll then be converted to kinetic energy, i.e. 1/2 mv squared. Okay, so what this is saying then is voltage B, or voltage AB, the energy required to move it from A to B, is the voltage of B minus voltage of A. So this would be, in our example, 6 volts minus 9 volts, which equals negative 3 volts? Is that right? Does that make sense? Maybe. Okay, I think so. So what this is saying is the amount of energy to move it from a particle, a positive particle, from A to B would actually give us energy. So if we moved a particle from here to here, we'd actually have more energy, which makes sense because we're moving in the same direction as the force from the positive charge over here. So this positive charge over here is helping push the charge away. And that moving in the same direction as the force will actually allow us to pick up energy. Another way of phrasing it is, so we have the potential energy from moving it to B minus the potential energy of moving it to A. And so we're going to lose 3 volts worth of potential energy. Now volts isn't really potential energy because you have to multiply it by Q. So work equals Q, amount of charge that you have, times volts. I kind of take this for granted. The mnemonic that I use is electron volts. So 1 unit for energy, make a little arrow. The dimension, one unit you can use for energy is electron volts. You can measure energy in electron volts. You're used to probably joules because that's the standard SI unit. But another unit that's available is the electron volt. And the way it works as a mnemonic is, you know, an electron is a charge, Q, and you know that a volt is a voltage. Really convenient that they both start with V and have similar names. Volt is a voltage. So using dimensional analysis, Q times V, work is QV. I'm going to look up electron volt real quick. That way I can actually give you the value electron volt. The value that we have for an electron volt. Hopefully it's measured in joules. Can I do it in joules? Mass, momentum, measurement, definition. Aha! So 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. And an electron volt is the amount of energy gained or lost by the charge of a single electron moving across an electric potential difference of 1 volt. So, we go back to this. If we have how much energy would be required to move an electron from infinity, I'm going to use positron because it makes it positive and it's easier. A positron, same charge as an electron, and same mass. Move it to 9 volts, how much energy would be required? Well, that'd be 9 electron volts. How much energy would require to move to 6 volts? 6 electron volts. How much energy would you gain by moving it from 9 volts to 6 volts? Well, you would gain 3 electron volts. Now, how much energy would you gain if you moved an electron, which is negatively charged, from 9 volts to 6 volts? Well, you would gain negative 3 electron volts, which would make sense. You would lose energy. So let's see, you have negative here. Nope. It would actually take energy to move it away because an electron right here would be attracted to the positive charge. So if you pull it apart, it just would act opposite that a positive charge would. Okay? So that's the general idea of potential. The big takeaway would be, one, the notation. So when we know that VAB equals VB minus VA, and that can then be rewritten as infinity to infinity, meaning the amount of energy to move a test charge from A to B equals the amount of energy required to move a test charge from infinity to B minus the energy required to move a test charge from infinity to A. And then the voltage is related to the electric field as this is just a multiplication, because the negative, you can have a dot product with vectors, but then the negative would be gone. So if you have the negative, then they're scalars. So the relation between voltage and electric field is negative integral E dot dr multiplied by dr. And then voltage of a point charge is K Q over R, single R. Okay? So now let's try some problems and work through them. Okay, first problem. A charge plus Q is uniformly distributed over a quarter circle, okay, of radius R, as shown above. Points A, B, and C, check, are located as shown, with A and C located symmetrically relative to the x-axis. Express all algebraic answers in terms of given quantities and fundamental constants. Okay? Rank the magnitude of the electric potential at point A, B, and C from greatest to least, with number 1 being the greatest. 2 points have the same potential, give them the same ranking. Okay, so rank the magnitude of electric potential. Okay, so electric potential, we're assuming, so the question is, which would take the most energy, A, B, or C, to move a test charge that's positive towards this positive uniformly distributed charged thingy of radius R. So it'll take the most energy to move it towards B, because B is the closest. So if we look at the equation for a point charge, we have V equals K Q over, where Q is this Q right here, over R. And R then would be that. So R is the smallest for B, so B would be the biggest. And then R for A and C would be the same. You would have to break up this into small parts to really do A and C, because there's different radiuses. You wouldn't know which radius to use. But you know that it's symmetrical for A and C. So even though we don't know the potential at A or C, we know that they would be the same. And the radius would, for pretty much every point, be larger for A and C. So we know that A and C would be larger. So we'll put 2's there. Okay, point P is at the origin as shown. Check. And is the center of curvature of the charge distribution. So is it B? No, not quite B. Closer than B. And there we got the second part. Move U up. There we go. Lock it in place. Haha. Okay. So now, determine an expression for the electric potential point P due to charge Q. Okay? So we know the equation for a point charge. So voltage for a point charge equals K Q over R. So for a small amount of voltage, we would have K small amount of Q over R. And we'll call this start, beginning. We'll integrate from over the whole thing. So we integrate for every small point of Q along here to this point P. then the end result would be our total voltage. Well, we know that R is going to be the same point for every single part of the curvature, which is why the question chose P specifically to be at the center of curvature. So what this becomes then is K over R can be pulled out, and we have delta Q, which is a small amount of Q in the middle. This then just becomes the total plus Q. This becomes V. So voltage equals K plus Q over R, where the plus Q is the symbol for total charge, not actually adding Q. We are actually multiplying by positive Q. So voltage equals KQ over R. Correct. Delete all those small delta Q's. All right, a positive point charge Q with mass M is, oh, I shouldn't have erased that. I think I'm going to have to use that again. I'm going to write that up before my short-term memory banishes it. So voltage equals K. I'm just going to write big Q. We know it's positive. And I'll use big R because I should be using big R. Okay. Placed at point P and released from rest. Derive an expression for the speed of the point charge when it is very far from the origin. Okay. So we're going to use energy. So I'm going to use work, which I know is energy kinetic plus energy potential. You don't have to write out this intermediate step. It's just to clarify things a little bit. These will be initial, goes to energy kinetic final plus energy potential final. We know that initially the potential energy will be Q times V, which will be, what was the charge? Point charge Q. Oh, convenient. Q times K, big Q over R. And we know that it's initially at rest, so the initial kinetic energy will be 0. It'll zoom off to infinity. So it says very far from the origin, very far, i.e. infinity. They just don't want to say when the particle reaches infinity because it'll never reach infinity. Therefore, you're talking about a time that doesn't exist. So they say very far. So infinity minus. So kind of infinity like that. It's kind of like 0 plus, which is kind of like 0, just bigger. So same idea. So they say basically infinity, and at that point the kinetic energy will be 1/2 mv squared. That's the equation we have for kinetic energy. So writing this up, brandishing my math skills with a Z. No, there's no Z-axis involved. This is completely one-dimensional. All right. And then we're looking for V squared equals KQQ over times 2mr, and then we will square root the whole thing, and there we go. I hope they asked for the speed at infinity, because if not, then I just solved for the wrong thing. We know K, we know Q, we know Q, we know 2, we know square root, we know mass, and we know radius. Okay, check, got it. Yes. So, and this is how I would do it. You probably could skip steps and just be like, Q times V equals 1/2 mv squared. But I like being extra, and it doesn't take that long to write out energy kinetic initial plus energy potential initial. Okay. Keeps me from making more mistakes than I need. On the dot representing P below, indicate the direction of the electric field at point P due to charge Q. Okay, so now they're changing tracks. We're going over to electric fields. So we have electric fields, and the big transition at this point is we're moving from we're moving from scalars to vectors, magnitude and direction. So look at this point here. A little delta Q goes that way. Ooh, that's a surprisingly straight line. A little piece of delta Q creates a electric field going that way. I'm not going to be able to live up to it. Yeah, maybe. That electric field from this delta Q goes that way, and the resultant electric field, green, goes this way. So they're all going to cancel out except for going to the right, horizontally. Oh, easy. I imagine question D is not worth odd points because that one is easy. Derive an expression for the magnitude of the electric. Ooh, this one is. Okay. So we need to find the electric field at this point. So for a small amount of electric field, you can tell that I'm going to go with an integration route. So we use Coulomb's law, K delta Q over R squared. And then we'll do integral. Yep, that seems reasonable. Now, the problem is, for any delta Q, we only want to include the horizontal component. So we're going to have to do, that's theta, so we're going to call this negative pi over 4, pi over 4. We could alternately do it with a more conventional, go in this direction, which that would be, this would be pi, it'd be pi minus pi over 4, which would be like what? 3 pi over 4, and then this bottom one would be 5 pi over 4. We could go that way. I'm just going to use negative pi over 4 to pi over 4. It might give me an answer that's backwards, like the wrong sign, but I know that the electric field goes to the right, and we're just looking for magnitude here. So we're going to go from negative pi over 4 to pi over 4, and cosine of theta. So now we need to relate delta Q to theta. So we know that delta Q is all the Q, but this theta, we're only using a quarter of the circle. So let's see here. This is over 2 pi, and this is over 1/4. Actually, I'm going to try and think of this slightly differently. So we know that we have 2 pi equals, let's say 2 pi theta equals 4q. And if we take the, let's see here, maybe a d theta. Is this right? I'm going to kind of play with this for a second. So then this would give us a dq equals 4q over 2 pi. Cancel that, would be 2 d theta equals q d theta over 2 pi. Nope, 2 is supposed to be on top. Okay, so I'm not quite sure a good way of justifying this, but the idea is that we're only covering a quarter circle here, but the angles covers a full circle. And so we have to ratio out how much Q is over how much of the circle is covered by Q. And so this is going to have to be something along the lines of, let's do a cosine theta. We'll do 2q over pi, and then over an r squared. And we'll still have the integral, and then a d theta. So when we convert the dq over to d theta, we're going to have a factor here. And, yep. So I don't have a really good justification why that is, but you're going to have a factor. And this would be the 4q, because it'd take 4q to go all the way around the circle. And you have 2 pi in the bottom for the full circle. Then we go negative pi over 4 to pi over 4. Pi over 4. And I have a whole bunch of stuff here. I am going to delete some of this. Whoop, whoop. And then we'll factor out things that are constant. 2q over pi. And then, so we're left with the integral of cosine of theta, which will give us, whoop, whoop, pretty sure sine, r squared pi, sine of theta. Yep, because the integral of sine of theta is, or the derivative of sine of theta is cosine theta. And there we go, which equals, so the sine of pi over 4 is square root of 2 over 2, but we have 2 of them, and one is negative, and we subtract one of them, and so we get 2 square root of 2, which gives us square root of 2. So we'll have 2 square root of 2 kq over r squared pi equals the magnitude of the electric field. And I can make it a vector and just say it's in the positive x direction. Okay, so that was how we found the electric field, by using, we had to use an integral, and then specifically we had to use cosine theta to make sure we took only the horizontal components of our vectors. And that was more difficult than the potential, because the potential was scalar. So one sort of pitfall or human performance trap that you should watch out for, because you would think that, well, we know that change colors, there we go, voltage equals negative integral E dot dr. We know that voltage, because we already figured it out, potential was K, I think it was Q over R, big R. Was there an R involved there? It feels like there should be an R. Oh, there it is. R squared. So you're thinking, okay, we just take the derivative of both sides and then the negative, and we could get the electric field. So we'd have electric field equals derivative, let's say with respect to R, negative of voltage, which equals, that's just the partial derivative. It's the same thing in one dimension. K, Q, R to the negative 1. I know, I went back to small r's. K, Q, R to the negative 2 times negative 1, which would give us, ignore the negative sign because we're looking for just magnitude mostly, kq over r squared. So what we're comparing here then, if we did this using trying to find the derivative of voltage, we would find kq over r squared compared to having this factor of square root of 2 pi in there. So 2 times the square root of 2, square root of 2 is like 1.4, so 2 times 1.4 is like 2.8. So this would be about 2.8 over 3.14, which is less than 1. So what we're saying is we can't use voltage because we don't take into account, we can't use voltage and then just take the derivative, because what we do is we lose information about this product, this dot product. This dot product does just the horizontal component, and that gives us basically how some of the vectors cancel out. And we lose that information if we just try and use voltage to find the electric field. We have to find the electric field by doing the whole integral. Okay? And that is how we do this problem. Let's do a couple multiple choices. Bam. There we go. And lock them in place. So for this one, let's see, and orange. Multiple choices go pretty quick. Granted, you only have, I think, 2 minutes? 2 or 3 minutes. I think maybe it's 3 minutes per problem when you're on the AP test. I think you have like 45 minutes for like 15 questions or something like that. So not a lot of time. Potential energy of the particle with plus Q, that one, due to the other two charges is, okay. So for this, start by writing up the equation. So for a point charge, so it'd be KQ over, I'll use small r. I know I vacillate between big R and small r. Does not converge. Sorry. We all have our failings in life. That one is mine, amongst others. So voltage due to plus Q equals K plus Q over R over A. V negative Q equals K negative Q over A. And so when we add these together, V total voltage, because we can just superimpose the two voltages, we get K over A times Q minus Q, which is 0. So another way of phrasing this is, how much energy would it take to move point plus Q from infinity down to this point right here? And the answer would be 0. If you look at this, so this is different because these are scalars, not vectors. Voltage is a scalar, electric fields are vectors. So looking at this as an electric field on how this is affected, we have plus Q goes that direction, and negative Q pulls a force in this direction. I'll call this force positive, force negative, and therefore force total is this direction. So when you bring it in from infinity, your thought process might be, well, which infinity do we bring it from? Because we have infinity in every direction. You can choose. They should all give you the same answer. So when you choose one, choose the simplest. So when you're thinking about this, work equals F dot dr integral, dot product integral. The R is in this direction, the force is in this direction, and therefore the theta equals 90 degrees. Or, if you want to be a little more sophisticated, pi over 2. Either way, the cosine of them is 0, and therefore you'll have 0 work done. Doesn't mean there won't be forces on it. It just means that to move that particle plus Q to that point from infinity will be, you can move the entire way with the displacement vector perpendicular to the force. And so A, 0. Okay? Next question. A metal sphere, i.e. conductor, with radius r1 has a total electric charge of Q, and a bunch of little pluses. I'm assuming they're evenly distributed on the surface, but not the interior. Uncharged metal sphere with radius r2 with r1 greater than r2. Okay. So basically it means there's more surface area on r1 than r2. Is then connected by a wire to the first sphere, as illustrated above. The separation of the spheres. Oh, so they're connected. Okay. separation of spheres is much greater than the radius of either sphere. Okay, much greater than. This is talking about that way you don't worry about induced charges. So prior to being connected, you don't have these pluses here, and you don't have pluses here. When they're connected, the pluses are going to rush over to R2. And the pluses over here aren't going to interfere with the pluses over here and create an uneven distribution. So what it's saying is these are two homogeneously, uniform distributions of charges on their surface. But I don't think that since they are different radiuses, radii, I don't think that the surface charge density, which would be a small amount of charge for a small amount of area, will be the same between the two. Because the goal of every little charge would be to position itself to minimize the total energy. Well, so that energy is equal everywhere, which will be the minimum for each individual particle. When equilibrium is reached, spheres will have charges on their surfaces of equal magnitude and the same size. No. The magnitude, the number of charges on each sphere will be different. I'm not sure how different, but they will be different. Charges on the surface will be equal magnitude opposite signs? Nope. They will all be, because all you're dealing with is either all positives or all negatives. They will disperse and be the same sign. So that part's definitely wrong. Equal electric fields at their surfaces. Maybe. I'm not sure of that one. Probably not. So I think that the sigma R1, which is the surface charge density, for the first one will not be the same as the second one. So I don't think so. Equal capacitance. We haven't talked about capacitance yet, but that's just going to be no. If you like, you can be like, maybe. Then you get to this last one, equal electric potentials. That's going to be true. And one thing that you'll learn when you talk about circuits is anything connected by a wire conductor will always have the same electric potential. Just like the electric field within a conductor will always be zero. The charges within a conductor will arrange themselves on the surface so that the interior will always have a zero electric field. Same thing, two conductors that are connected by a wire, i.e. another conductor, will always have equal electric potentials. And one way to visualize this is, you could say the opposite. Like, well, maybe they don't have the same electric potentials. Basically meaning that it would take a different amount of energy, to say 9 volts, I like 9 and 6, to move it to 1. This is not true. So this is the counter example. To move a test charge to 1 or 6 volts to move test charge to the other one. Well, since these are all, an electron can move almost freely throughout the conductor. It's the whole sea of electron idea. It's not exactly zero, but it'll be 0 plus, which is basically zero energy to move a charge or an electron throughout the conductor. So what you could do then, if this was true and you had 9 volts here and 6 volts here, which it's not, but if it was, you could take an electron, move it down here with a cost of 6 volts, and then it can migrate over to here and be at a 9 volt position. And what you do is you basically gain 3 volts worth of energy, electron volts. I'm calling voltage energy and referring to it as energy. It's not, but it's convenient for speaking. So you would gain, at a cost of 6 volts, you'd gain 3 volts of energy just by moving along, going to this one first. Or if you went to the far one at a cost of 9 volts, you could then, the electron then can migrate over to the 6 volts and lose 3 volts of energy. That you can't, it's completely inconsistent with life. That would create some sort of infinite energy machine. And that's pretty taboo in life. So that's kind of a counterexample of why it's not possible. So if one of these is 6 volts, the other would have to also be 6 volts, or 9 volts and 9 volts, whatever you choose. The point here is both spheres will have to be at equal potentials because they are in contact with a conductor. So, okay, we have a few more potential problems we'll work through. We'll work through those guys next time, but this is kind of the basic of what you need to know. Appreciate you guys sticking around, and I will see you next time.